Hi everyone, it's my pleasure here today to present our paper WaterBear, Asynchronous BFT with Information Theoretic Security and Quantum Security. So Byzantine fault-tolerant BFT is a fundamental building block for blockchains. It is known as a core primitive for permissioned blockchains and is increasingly used in permissionless blockchains as well. Based on the timing assumption, BFT can be categorized into three types. And among them, asynchronous BFT is the most robust type of BFT. Another thing is, if we consider the security model, there are in general three types. In computational security, the adversary is restricted to probabilistic polynomial time, and in information theoretic security, the adversary is unbounded. Computational protocols assume the hardness of some intactability problems. And these mathematical problems may in the future be proven to be broken or weakened due to newly developed techniques such as quantum computers. And in contrast, information theoretic security provides everlasting security, typically assuming secure or authenticated channels only. And meanwhile, it's an important problem to design a Byzantine resilient protocol relying on no public key cryptography, PKC, considering the efficiency and quantum resilience of symmetric cryptography. And in this work, we are interested in both information theoretic security and quantum security. And we study asynchronous BFT. There are several classic asynchronous BFT paradigms. Among them, the BEAT.Our paradigms by BEAT.Our, Kamler, and RABA, and the CKPS paradigm by Boxin, Kamler, Petzold, and Schrupp are the most well-known ones. Each is followed up by several practical works proposed recently. For instance, Haibin BFT, BEAT, EPIC, and Red Valley fall into the category of BEAT.Our. And the protocols such as Dumbo and Speeding Dumbo fall into the category of CKPS. And in CCS 2022, our group proposed the PACE paradigm that improved upon BEAT.Our. So the core component of the PACE paradigm is what we call RABA, reproposable asynchronous binary agreement protocol. So we extended the ABA, asynchronous binary agreement protocol, to the notion RABA, reproposable one. The RABA has a nice feature that if at least f+1 correct replicas propose one, all correct replicas decide one. It also has a coin-free fast pass here, where nodes do not need to toss a coin. As a result, PACE is able to enjoy parallel RABA phase and achieves much higher performance compared to the PKR counterparts. In our work, our starting point is the PACE, and we want to somehow convert it into the information theoretic secure setting and quantum secure setting. So if we take a closer look at the components here, we need to look at both RBC and RABA. And RBC refers to reliable broadcast. And in fact, there are already a lot of choices here. Say, in the information theoretic setting, broadcast broadcast is a choice. So the idea of broadcast broadcast is that it carries message payloads in every single step. So it's information theoretically secure. It's not that communication efficient. So another choice is the city RBC due to Cashin and Tessero. So it relies on hashes, in particular Merkle tree, to build the RBC. So it's quantum secure, but not information theoretically secure. It's more communication efficient compared to broadcast, and it's being used in a lot of recent practical works, such as Honey Badger, BEAT, and Dumbo family. And in this work, we use broadcast broadcast to build our information theoretically secure protocols called WaterBear, and CTRBC to build quantum secure protocols, and we call them WaterBear QS. Note that we can use some of even more recent development to achieve the same goal, such as error-free BRB, which is information theoretically secure, and Sisi BRB, which is quantum secure as well. Another thing is we look at ABA. The main challenge here of building information theoretically secure BFT is that most efficient ABA protocols are built from common coins. In common coins, all nodes toss the same coin, and it's usually instantiated using primitives such as threshold signatures or threshold pairs. These primitives are not information theoretically secure or quantum secure. So in our work, our WaterBear work, our solution here is to avoid the use of counterpoints and use local coins instead. Namely, in local coin-based ABA, every node only needs to locally flip a random coin and obtain a value when needed. So this does not need any interaction with other nodes to negotiate the counterpoint at all. And in fact, the only known ABA from local coins is due to Braccia's ABA, proposed in 1984. Braccia's ABA involves 3 phases of unparalleled RBC instances. So the idea is that each node reliably broadcasts its vote in every single stage. So the protocol again has n-cubic messages. Compared to common coin-based ABA, local coins appear to be impractical, and local coin-based ABA is never used in any practical systems at all. Our goal here in this work is thus showing that one can still build practical protocols by using local coin-based ABA. And here, our goal here is to build more efficient ABA protocols, and we want to avoid using coins as much as possible. So indeed, if local coins is cured with probability of 1 over 2 to the power of n, all replicas can cure the same coin, which can be very expensive. So we want to avoid going to that route as much as possible. So we want to build a protocol with coin-free fastpass as well, so coins are not cured unless they are really needed. Our pathway is shown in this slide. So in terms of ABA, we first improve Braccia's ABA to cubic ABA. Cubic ABA also achieves an cubic message. Compared to Braccia's ABA, the contribution here is that it reduces the number of steps and only involves cubic communication in one of the phases. Then we further improve cubic ABA to quadratic ABA. Quadratic ABA reduces the message complexity to n squared, and it only has 4 steps in the fastpass. So both protocols are shown to be very practical compared to Braccia's ABA, and we show that we can use it to build practical information theoretically secure BFT and quantum secure BFT as well. Another nice thing is that our ABA protocols are generic. If the local coins are replaced by weak common coins or common coins, we can immediately obtain more efficient ABA protocols compared to existing state-of-the-art. So here, weak common coin refers to the type of coins such that with certain probability, all replicas cure the same coin. And the idea is we can directly replace the coins using weak common coins or common coins, and we already obtain more efficient ABA. And these protocols can benefit other practical asynchronous BFT protocols and other protocols in addition to BFT, such as distributed key generation and multi-party computation. So in this slide, I briefly show the ideas behind the cubic ABA and quadratic ABA. So I don't want to dig into the dirty details of how we prove the correctness and how we build the protocol. In general, cubic ABA, we want to replace the unparalleled RBC instances as much as possible. So we replace the first 2 phases into all-to-all communication. So the idea is that as we do not curate parallel RBC that often, we can improve the performance as well. But still, in the 3rd phase, we realize that RBC is still necessary to ensure that all replicas eventually converge to the same decision. And in quadratic ABA, our idea is to further replace the parallel RBC into all-to-all communication. So the general insight here is that any voted value needs to be confirmed. And for confirmed, what we mean here is that everybody needs to count the number of votes from the previous step to finally convert the result. So as a result, we build a very efficient ABA that only has n-squared communication. And finally, in order to build WaterBear protocol from the PACE framework, we also need to convert the ABA protocols into RABA protocols. We in general follow our insight in the PACE work for the conversion. And our conversion is very efficient. We do not introduce any additional cost at all. But when we convert the protocol into RABA, we realize that there are still some nuance, some challenges when building the protocol. So proving the correctness needs extra care as well. But we finally did it, and our protocols enjoy several benefits. It enjoys the benefit of RABA, such that if f+1 correct replicas propose 1, all correct replicas decide 1. Another thing is that it also inherits the benefits of ABA, such that it has a coin-free fastpass, and it actually immediately meets all the needs that we wanted for building information theoretically secure BFT. And in this slide, I briefly show the pseudocode and our insight here. So the idea is that when we build RABA, we only need to change the first round of the protocol, so we do not need to change the generic workflow of the protocol at all. And we finally built RABA for both cubic ABA and quadratic ABA. And we use these two choices and our RBC choices to build 4 WaterBear protocols: WaterBear C, WaterBear Q, which are information theoretically secure, and WaterBear QSC and WaterBear QSQ, which are quantum secure. So we implemented our protocols in Golang, and we also implemented the BEAT protocol in the same library for a fair comparison. We evaluated them on AWS using up to 61 instances. And in this slide, I show some evaluation results. And our results show that WaterBear protocols have similar performance as BEAT. And when n grows larger, WaterBear protocol underperform BEAT. But all WaterBear QS protocols outperform WaterBear and BEAT. For example, when n is 16, there are 16 nodes. WaterBear QSQ has about 1/8 latency and 23% higher throughput compared to BEAT. And I think our results show that building efficient quantum secure asynchronous BFT is possible. And to quickly summarize our contribution. So here in this work, we proposed actually 2 new ABA protocols and 2 new RABA protocols, and they are efficient local point-based asynchronous binary agreement protocols. And we can also improve upon existing ABA protocols from common coins and weak common coins as well. And we use these ABA and RABA protocols to build very efficient asynchronous Byzantine fault-tolerant protocols with stronger security guarantees, achieving security in the information theoretical setting and quantum secure setting. And our evaluation results show that we can actually build very efficient quantum secure protocol and information theoretical secure protocols as well. And that's all for my talk, and I'll take questions from here. Thank you.